Okay, so we're gonna start up here again. Sorry for that brief interruption. Whenever something is raised to an exponent of 0, it just means that the concentration does not affect the rate, because anything raised to an exponent of 0 is equal to 1. So here's just showing you graphical data based on the order. So when it's 0 order, as you can see in the first graph here, it's showing you that the concentration of the reactant does not affect the rate of the reaction. When it's first order, it's directly proportional. And when it's second order, as you can see, this is the relationship between the concentration of that reactant and the rate. So it's exponentially growing. And then the graphs below are showing you the concentration versus the time of each reactant. Okay, so we're gonna do a sample problem. Here's the reaction: 2NO plus 2H2 forms N2 plus 2H2O. Remember, the rate of reaction is not determined by the products, so we can ignore this part right here. All we care about are the reactants. So as you can see in this graph, they did some experiments, and this is shown for you. If we take a look at our textbook for a second. In the textbook, remember, you should also always be reading the textbook as well with every note, just to get a further understanding. It's showing you a picture here of a chemist who is doing several trials, reacting the concentration of a reactant and measuring the rate of the reaction. So she does trial 1, measures the rate, trial 2, measures the rate, and trial 3 measures the rate, and then she comes up with a chart, which was what we are going to be looking at right now. So here's this chart. They reacted NO with H2. In the first trial, they reacted 0.4 moles per liter of NO with 0.1 moles per liter of H2. And the rate of the reaction is shown here. They found out it was 1.1 times 10 to the negative 5. Then they repeated the experiment, so trial 2. This time they changed the initial reactant of H2 here, and they got this rate of reaction. So our job right here is to figure out what is the rate law for this experimental data. So before we go to the next slide, I'm going to be walking you through how to do this on paper. So here, what you have to do first is you have to find one reactant that's remaining constant. So in terms of, when we're trying to find the exponent for NO, the first one, you have to make the other one constant and see how this one is changing. So if we're trying to find, so let me repeat there. So if we're trying to find NO's exponent, we don't know its exponent, okay? You want to make sure H2 is constant and see how this is changing. So you find the trials where H2 is constant, which is trials 2 and 3, okay? And then we look and we see how is the concentration of NO changing. So from 0.4 to 0.8, how is it changing? So you simply just divide 0.8 divided by 0.4, and you should get times 2, okay? And then you see how that affects the rate of reaction. So this is why this has to be constant, because we're only looking at how NO is affecting the rate. So you do 8.80 times 10 to the negative 5 in your calculator divided by 2.2 times 10 to the negative 5, and you should get 4. So how do we figure out this exponent from this data? So you do realize that you're figuring out 2 to the exponent of something equals 4. So hopefully you guys realize that 2 to the exponent of 2 equals 4. So that's the answer to M. So M is 2. Okay? So we know the first answer here. Okay, so when you write out the rate law, you always write rate equals K, which is a constant, times the concentration of the first one, raised to the exponent And now we're going to figure out the second one. So when you're trying to figure out H2, you want to find the trials where the other one is constant. So in this case, NO is constant in trials 1 and 2. So we're going to look at those two trials, and it's going to be written in red. Okay, so from 0.1 to 0.2, it is multiplying by 2. And then when you divide this number by this one, 2.2 times 10 to the negative 5 divided by 1.1 times 10 to the negative 5, you also get 2. Okay, so when we're figuring out this exponent, so this time we're trying to figure out H2's exponent, which is n. Okay, so how do we figure that out? So we just figured out that it's going 2 to the exponent something is equal to 2. So hopefully you realize that 2 to the exponent of 1 is equal to 2. So therefore, n is 1. And I wrote that here in the rate law. The answer is H2 is raised to the exponent of 1. Okay? So don't worry if this is kind of confusing right now. It does take a few examples to walk through to understand, and you do have to practice this after in order to consolidate it further. Okay, so let's go to the PowerPoint again. So it explains it all in the PowerPoint on the next slide. It says choose 2 runs with identical concentrations of one reactant A while the other reactant B is changing, and then see the effect of that change on the rate of the reaction. So it explains that from runs 1 to 2, it was staying constant while H2 changed from 0.1 to 0.2. And then therefore the order is first order for H2. Okay, and then it explains how I did the second step too. Okay, so now we're going to determine the rate constant. So the rule to do that is you try to choose one trial or run and plug in all the data from that trial into your rate law equation and solve for K. So I'm going to show you the process right here. Okay, so we're going to pick a trial and we're going to plug in numbers. So you should be writing this part down, so I will leave it on the screen for a bit. Pick a trial and plug in numbers and solve for K. So we are going to pick trial 1. So trial 1 is right here. And we're going to write out the rate law. So rate equals K times NO2 to the exponent 2 times H2 to the exponent 1. And then we're going to plug in all the numbers from that trial. Okay, so the rate is right here. 1.1 times 10 to the negative 5 equals K times 0.4 squared times 0.1. Okay, and then you simply isolate for K. So right now we're not doing the units, we're only doing the numbers, and then I'll show you how to do the units after. So you're isolating for K, so K equals 1.1 times 10 to the negative 5 divided by 0.4 squared times 0.1. Okay, so you simply plug that into your calculator and you should get 6.875 times 10 to the negative 4. Okay, so that's the number value. Okay, so when you're solving for the rate constant, you also should have units. The way I do it is I solve for units separately. Okay, so for units, again, if you want to write this out clear, you're doing rate equals K times concentration. Okay, so therefore K equals the rate divided by concentration. Right? So I'm just simply plugging in the units now. So the unit for rate is moles per liter times second divided by, so I change this line here to be divided by and then square bracket, and then I'm showing you the units for concentration is moles per liter, and M is 2, times moles per liter, and then I close the square bracket. Okay, so now it's just simply algebra. So moles per liter times second, and then I changed the divide sign to a multiply sign, and then I flipped it. So I went 1 over all of this. Okay. The next step is I combine this part. Mole squared times mole is mole to the third, and liter squared times liter is liters cubed. Okay. And then the next step, you notice here, this is kind of messy, 1 over mole cubed divided by liter cubed. So I simply just flipped this to be liter cubed over mole cubed. Okay, so this part right here, I just crossed out like units that are in common. So moles crossed out with moles cubed, and what I'm left with is moles squared down here, because 3 minus 1 is 2. Remember, exponents, you subtract exponents when you're dividing. And then liter cubed minus liter 1, or there's a little 1 here, so you get liter squared here at the top. Okay, and you're left with seconds on the bottom here. Okay, so what you're left with, I rewrote it over here. What you're left with is liter squared divided by moles squared times second. Okay, so therefore your whole K value is 6.88 times 10 to the power of negative 4, and then these are our units. Okay, so let's go back to the screen here. So units for K, we just solved for a third order reaction, so the challenge has already been done there. So maybe you can practice it once more, trying to solve for the units of K for a third order reaction. But generally when you have a 0 order reaction, this is the units. First order reaction, this is the unit of K, and then second order reaction, this is what it looks like. Okay, so we are gonna practice now. So if everybody could go to page 380, number 3. Okay, so on page 380, I do believe this is page 380. Yep. Number 3. Okay, I want you to try this one. So here's the reaction represented by the balanced chemical equation. 2NO plus Cl2 forms 2NoCl. The initial data from these runs at 25 degrees Celsius is represented by the following chart. So our first step is to look for one reactant that remains constant. So you're going to start with runs 1 and 2. So notice how NO is constant here. So you're going to look at the change in Cl2. So what is happening from here to here? 0.1 to 0.2. Hopefully you see that it's multiplied by 2. And how does that affect the rate? So what is 0.36 divided by 0.18? And it is 2 as well. Okay, so because both of them changed by a value of 2, therefore the exponent is 1, right? Because 2 to the exponent of 1 is 2. So therefore, the order of reaction for Cl2 should be 1. Okay, so let's try NO now. So find the trials where Cl2 is constant. So that's trials 2 and 3. Okay, how is it changing for NO from 2 to 3? It's being multiplied by 2. And then here, what's happening? You take 1.44 divided by 0.36, and that's 4. So a change of 2 is affecting the rate of the reaction by 4. Therefore, the exponent is 2, because 2 to the power of 2 is 4. Okay, so therefore NO is raised to the power of 2, and Cl2 is raised to the power of 1. Okay, hopefully you guys understand that part. Okay, so that was one practice question I took up with you, but you should try the other ones as well, and the answers are given there beside the textbook. Okay, so now you just want to practice the homework, page 382, number 1 to 4, and I will take up any questions we have on Monday when we schedule our Zoom meeting. Okay, good luck and stay safe. Bye.